So let's say this takes about 1 Newton to push it, and let's push it, I don't know, about half a meter, which is a little further than this, but just as a demonstration. So we basically need to know how much work we're talking about, which is actually measured in joules. So that's amount of energy, right? So how much work is going to be equal to our force, okay? And again, it's about 1 Newton of force, and then how far we push it. That makes sense, right? So yeah, so we're going to be in physics, we're going to be looking at energy, talking about energy, which is measured in joules. And this is our first formula that we're going to be doing. You're going to be doing some problems with it in the physics welcome assignment. All right, so this exerts a force of about 1 Newton. 100 grams exerts a force of about 1 Newton. A kilogram exerts a force of about 10 newtons. Okay, so this is about 10 newtons, just so you can get that concept. What is a Newton? A Newton is a force, okay? And of course, on the Earth, we have this mass. So you have some mass, and of course we have the Earth's gravity pulling down on this mass. And so again, this mass of about 1 kilogram, it's approximately a kilogram, is going to be about 10 newtons. This mass of 100 grams is going to be about 1 Newton. And we might be asked, what if we had, say, something that takes a force of 1 Newton, and what if we pushed it a whole meter? And this is so tough, pushing this a whole meter. Okay, let's continue. Okay, Science 10. So yeah, we're going to start physics. What we've just seen is what's really critical, understanding what a Newton is. It's a force exerted by anything with mass. And you saw that a 100-gram apple exerts approximately about 1 Newton. And, say a 1 kilogram textbook around about 10 Newtons. Now, we're going to be using that formula right there, work, which, is energy, right? Work and energy, same thing. Work equals force. How much force you put into something and how far you push it. So that's going to be our start in physics. Physics is all about motion. Let me share my screen because you want to make sure you're ready. You want to make sure you've got a notebook and you've got a calculator. So yeah, you definitely need a calculator. You want your notebook. There are practice questions that go with this, and you absolutely have to finish those first before you do the welcome assignment. But definitely make sure to print your physics formula sheet. And there's that first one. We already started talking about work equals force times distance. And yeah, we're just going to get into this right now. Let me maximize my screen. Make sure you've got your notebook, your pen handy. And yeah, let's write this down together. Physics, it's all about motion, so moving. So that's something that we're all familiar with. Requires energy, right? Motion requires energy, especially if you've got anything made out of mass. So in other words, matter. Now in physics, chemistry as well, science, energy is measured in joules. Make sure to get this down. These might be some new words, but you're going to want to make them your new friends. Joules, that's just the unit. Here's the critical concept. Work equals energy. Okay, so work equals joules. You need energy to do work. And of course, as we just said above here, this is indeed joules. So get comfortable with, work is joules. Joules is work. We're always going to be doing our distance in meters, m. We're going to be looking today at concepts like velocity and speed. You're going to think, well, those are the same thing. Speed is not as accurate, meaning I don't tell you which direction I'm going. I just say 40 kilometers per hour. For this one, I say 40 kilometers an hour, south west. So I give you not only the magnitude, but I give you direction. And, so example again of just magnitude, 40 kilometers an hour. But if I told you go 40 kilometers an hour, that wouldn't be enough information. So velocity is a bit more detailed. And of course, these are both, though, also measured in meters per second. Okay, so this is really, really critical, knowing some of the units that we use: meters, seconds, joules. And of course, joules is energy. It takes a force. Okay, so motion requires energy. It takes a force to move something. This concept of force, that's in Newton. I'm going to write that down underneath. It takes a force to move. We're going to move a mass. Whether we push the mass or whether we lift the mass above our head, right, against gravity, it's still going to take a force. In fact, gravity exerts a very specific force. Look at that in the unit. Newtons. Here's another unit that we use, newtons. So you need to start getting a handle on, start thinking about some of these units: meters, seconds, joules, newtons. Joules of course, work, newtons, force. So push on something right now. You're writing some notes, but take a moment and lift up a textbook. And that'll take some newtons to do that. So we're also going to look at distance and displacement. Okay, so let's take our little runner here and, run around a standard track. Standard track is 400 meters. Okay, so that would be your distance, and then you're going to stop right there. So you're going to come back to exactly where you started. So your distance could be 400 meters, but your displacement will be 0. Displacement, what's my difference between my starting point? So if I started right here and I stop, if I start and stop in the exact same place, I have no displacement. Displacement is 0. So those are the things we look at with displacement. And indeed, if you just ran one lap around a circular track, your displacement would be 0. Your distance, well, as long as it's a standard Olympic track, be 400 meters. Good job, by the way, for that jog you just did. Couple more examples here quickly on distance. Distance, I might tell you, hey, there is a treasure. It's 50 meters from you. That's not enough information, especially if it's a really important treasure. But if I give you displacement, I give you not only the magnitude, so the 50 meters, but I give you direction. Okay, so go get that treasure. It's 50 meters exactly, 50 meters east and exactly east. So yeah, get out your compasses. No, I haven't done that. I haven't buried a treasure by your place. So you could check. Maybe I did do that. We're going to also look at average speed. This is actually the formula for average speed. We're going to get into this right off the bat here. Distance over time. You say this all the time when we're talking speed. Hey, what's the speed limit? 50 kilometers. There's the distance per time per hour. It's right in. You already know this formula. You've been saying this formula all your life, or at least ever since you started driving. Okay, let's talk about that apple that we saw right at the beginning. I was showing you, and yeah, let's move that apple. Let's push it. Let's push it a couple meters. So let's take a look at that apple, because to push that apple is going to take some energy. It's going to be some work. How much energy, work in joules equals a force. Okay, well, for the apple, it was just 1 Newton, right? Times the distance. Let's move it 2 meters. So yeah, so let's see here. Let's figure this out. A force of 1 Newton is applied to an apple, and the apple is pushed 2 meters. How much work was required? Well, when we're solving problems like this, first of all, just summarize the information, kind of focus in on it. This helps me focus. What am I given here? Well, I know the force. It's given right in the question. it's about 1 Newton of force to push this apple. Do I know distance? Yeah, I know distance as well. Distance of 2 meters. Okay, that's definitely going to take some energy. And what is required? What is the question asking? And this is how we solve problems in physics and math. We're looking for the work. We're looking for the joules, right? Remember, we were just talking about that unknown number of joules. We're going to do a little analysis and figure out what formula. And of course, the formula for work equals force, which we have right here, times distance. Write this down with me. You can also press pause and just kind of take a look at what I'm doing here. I've taken these words and I'm summarizing the information. What's given in this question? What's required? What's the question even asking? And then do some analysis. What formula do we need, right? And now we just solve it. We just plug it in. We're just going to plug it in. So work, the number of joules equals force of 1 Newton. Put your units times distance of 2 meters. 1 times 2. Oh, yeah, I can do that in my head. Cool. 2 joules. There we go. That's how much energy it takes to move and to push. If there's 1 Newton of force required, and that can actually be measured. In fact, newtons are that amount of force is used to measure how strong a shark bite is, how we estimate how strong T-Rex's bite was, bear bites. Now, of course, these scientists aren't set out and said, hey, stick your hand in the mouth of a shark and stick your hand in the mouth of a bear. But just so you can get a sense of what a Newton is, push on anything, and move it, right? And so basically there's going to be a certain number of newtons you're using to push that, whether you're pushing it straight up or whether you're pushing it along a table. And who hasn't pushed an apple 2 meters on a table? So if you've done that recently, you've used 2 joules of energy. So yeah, so go ahead and push an apple 2 meters. It's going to take you about 2 joules of energy of work. All right, so let's talk about pushing a box, because that's not many joules. Let's push a box here. Okay, and looks like we kind of have it solved over there, but let's see here. And again, work equals energy equals joules. So Ted pushed this box with 15 newtons. Ooh, and did 300 joules of work. How far did he push it? Again, let's analyze the question carefully. What information is given? What's required? How far did he push it? Okay, so distance. Distance. I'm looking for distance. Unknown number of meters. Good job, by the way, Ted. Looks like he's working pretty hard here. What do we know? What's given? My force, or my newtons, right? Because force is in newtons. And it's 15.0 newtons. Okay, so 3 significant digits. And my work. Oh, actually, I know the work here. 300 joules. But again, I don't have my distance. That's unknown, but that's what I got to solve for over here. Well, I'll first do a little analysis and see what formula for sure that we need. When we're solving problems like this, it's reading it and trying to figure out which formula from your formula sheet. And given these 3 things are in the question, it's this formula. Work equals force times distance. And that's how you do any of these questions. You look at the words, you pull the numbers out. What is the given numbers? You pull the actual question out in as little words as possible. Okay, find distance. And then we look for the formula that'll do that. Now we got to do a little bit of rearranging, right? So this is F times D. We're going to divide D out. So distance equals work divided by force. You can just add that to your formula sheet right now, really, right? That this is indeed, I'm just going to grab my notes here. Yep, I'm on track. Let's solve this because we have our given information. We know what's required. Find distance. How far did he push it? I've checked my formula sheet, and indeed, it's going to be work equals force times distance, but I got to get distance all alone. So distance equals work over force. Add this to your formula sheet, guys, so you know how to solve for distance.
But yeah, my distance here equals how much work good old Ted put in, 300 joules, and divide it by the force, 15 newtons of push. Oh, not 150, come on, dude. 15.0 newtons. Put those units there too, always put the significant digits that they're using. And indeed, this works out to 20 meters. There's our answer, put a little box around it. Hey, good job, that's pretty far. Really want to congratulate Ted on his work there. And you're right away seeing how we solve physics problems. We figure out the given information, what's required, do a little analysis, figure out what formula, and then just solve it. Just plug the numbers in, and yeah. So we have force, right? And force is to move objects. To move any object, you need to exert a force. So kind of put yourself in Ted's shoes, literally right now. These nice gray shoes of his, really beautiful shoes there, Ted. And anyway, so it's a force to move some objects, and you do need force. You need some newtons to move an object. The work is, or the energy, right? It's the joules. How much energy? Well, how far do we push it, right? Like if he just pushes it an inch, that's not much energy. But he's going to push it like 20 meters. Well, hey, that's going to be like 300 joules, as we can see. So to get work, right? Work, how much work? Write it down with me and kind of say it, kind of think about it. This makes sense. Work, force, how hard I push times how far I go. Okay, let's talk about energy a little bit more. Like we're diving right into this, but let's just take a look at energy. I'm going to flip the slide here. Think about energy now, right? Good old Ted's putting in energy for sure. All right, so energy is indeed measured in joules. You're going to want to get that down. You might have already written it. You probably should have, but put it down again. Energy is measured in joules. It's this guy right here, James Prescott Joule, got credit for discovering mechanical equivalent of heat, because heat is energy. And with the steam engine, right? You can get a bunch of energy and turn it into a train going down the track. Energy is energy, right? The unit is the joule. If we are pushing a box, that's going to take energy. If we're lifting something over our head, it's going to take energy. This has kinetic energy. That's actually even one of our formulas here. So we can see joules right here in one of our formulas. So energy, you'll see it right here, EK, kinetic energy. This is covered later in the physics unit, but ultimately, the mass of this car and its speed, that makes sense, right? If the car is just kind of barely moving, and sort of accidentally bumps into, I don't know, like a pylon, it's not a big deal. But if the car is going really fast, and also, whatever its mass is, cars are always heavy. And last time I lifted a car was never. So basically what we got going on here, if this car is going fast, and then its mass, and then, it's going to have a lot of kinetic energy, a lot of energy. Energy is energy. Thanks, Mr. James Joules, JJ for short. Let's write down some of this information. We'll also kind of look at some of these notes that I just have beside there. But indeed, write this down. Energy, and think about it as well, is measured in, fill it in, right? Good old joules. Again, thanks. To push a box, or to push something. Push a box. We'll talk about pushing up in a second. It's basically the same concept. Work, it's going to take work to push that box. How much force, because it could be a big box or a little box, it could be just an apple, times how far did you push it, right? Distance. Up. Hey, this is kind of cool. This is also on your formula sheet. I want to show you this one on your formula sheet right there. E.g., gravitational potential, energy, mass against gravity times change in height. That's what this guy's doing right here. He's taking this mass and he's changing its height, right? So maybe it's, I don't know, maybe somebody helped him get it to there, and then boom, he's going to send it up, I don't know, about 50 centimeters or so or something, right? So basically he's got mass times gravity, because he's got to lift it against gravity, change in height. We'll look at that later, but I just want you to know that right now, that's how we actually figure that out. And it's cool how we write it, like e.g. gravitational potential energy mass. I don't know, we'll call this guy Matt here. Matt is lifting the mass against gravity, and he's got a change. That's what this little sign means. And we also call it delta, delta H, change in height. Job, Matt. Well done. James Jules, look at him. He's happy with these guys. This is probably still Ted there. James is very happy with these people. Okay, so we're going to talk about how to solve these types of problems, right? And again, if you are using a formula, and this is our main one we're doing right now, where work equals force times change in distance. So in other words, our joules equals how many newtons times how many meters we go. Okay, so hey, we got a question right here. We're going to exert a force of 25 newtons. It must be a little bit heavier textbook, this one, while lifting it to a height of 1.4 meters. So just to even start lifting it, like it would still be 25 newtons even if you lifted it 1 inch or 1 centimeter or whatever, but you're going to put in 25 newtons all the way up, 25 newtons at 1.4. How much work? Okay, they lift this textbook. Good job, by the way, on lifting that textbook. And so let's solve this one. How do we solve these, right? We've already seen this. Here's our method. What information is given? What information is required? Do some analysis, what formula? Then we just do the math, and then we answer it in a sentence. So I'm going to go over here. There's a problem. Call it a model problem. We got a little car going on here. Let's move the car out of the way. That was interesting. I left my car in the notes. Okay, so you're going to want to probably pause the video, write this question out. So just hit pause, write it out quick. Okay, you paused, you finished writing it out. What information is given? Right underneath, what information is given in the question, what is required? Just write these out first. You don't need to kind of just kind of take it slow, kind of go step by step. I actually often like to start with what's required. What does the question actually ask? How much work? It's right there. So I want to find work, or unknown number of joules. So we're looking for work. That gives me a hint what formula. I may not know just yet, right? So also you got your formula sheet right beside you, but you're just kind of taking it step by step. Yeah, we're looking for work. Okay, what information are we given? We got 25 newtons, so we got a force. Force of 25 newtons, right out of the question. So we take away the words. It makes it easier to solve. Look at all these words, all these letters. Take away the words and letters. Okay, force, 25 newtons. Okay, we got a height, we got a distance there then, right? Distance, we lift it, 1.4 meters. And again, I don't know the work, right? The question actually asks that, unknown number of joules. Okay, do some analysis. Again, this grasp method, I'll just zoom out a little bit so you can see our problem-solving method. What information's given? Again, get rid of all the words and just have the numbers. What's required? What is the question actually asking? In this case, how much work? Analysis, basically what formula? We already have a really good idea that it's going to be the work formula, right? Because work equals, force times distance. Then we just plug the numbers in, and then we're just going to answer it with a sentence. And that's what you do for all of these types of questions. You're going to be doing a lot of these for practice and for marks. Okay, so analysis, work is equal to force times distance. Solve this. So we'll just basically plug in the numbers now, which is nice when we get to this stage. So work, No, we don't know it. Question asks for it. Force of 25 newtons times 1.4 meters. We lifted it up. Now, just take a moment. I know you're writing this out, but finish writing it out. Remember, a single kind of 100-gram apple, 1 Newton. So this is a fairly hefty textbook, 25 newtons. And you're lifting at a pretty good distance, but that's the force it exerts in your hand as you pick it up, and there's 25 newtons there. You can feel it, and we want to know how much work that is. So we just multiply those two numbers together, right? So make sure you absolutely have to have a calculator, okay? So make sure you got your calculator. So we're going to go 25 times 1.4, 25 newtons times 1.4 meters, 35 joules, because it's work we're looking for, right? So our answer, work, is equal to 35 joules. Paraphrase it. Paraphrase that, and basically it takes 35 joules to lift the textbook. I'll just call it a text up 1.4 meters. Done. Cool. Use that method all the time. You're going to be practicing this over and over. You could redo this question again right now, just on your own. Pause the video, cover up the answer, try it again just to make sure you've got it. Okay, so that's how we solve. We got some more practice questions for you. Let's show them. These practice questions, you can pause the video and try them. They're also in Moodle, and along with where they're at, they're right there in Moodle. It's the teaching video 3-1, for our physics welcome to physics video. Those questions, all these questions are there, plus links to other videos on how to solve them if you need some help solving them. Do all of these, okay? So the links to the answers in the video is all in Moodle. So yeah, hit pause and then do that. and then basically come back and let's continue with this, because yeah, next we're going to look at something called scalars and vectors. I know you're thinking that's totally awesome. And so let's look at that. Scalar and vector? Can't wait. Okay, scalar and vector. You're going to see right away what these are, but let's just start with scalar and definitely write this down. Scalar is a magnitude, but no direction. Okay, so if we just say that this car is going 80 kilometers per hour, if that's all we say, that's a scalar. Okay, it's only magnitude, right? There's just magnitude there. Now we got this guy standing here, and all we say to him is go 5 meters, right? So go 5 meters. Which way? Should he go? This will be west here. Should he go west? So if that's west, then this way would be north. Okay, that'll be east coming back at us, and that'll be south going there off to his left. There's just a magnitude. There's no direction. Oh, so a vector has more information. A vector would actually tell him which way. But these are just scalars. Just magnitude only. So let's write that out as well. I'm sure you have already, but I'm just going to write it out. Scalar, magnitude only. Okay, versus vector. Okay, so let's take a look here at some vectors. Scroll up. So now we gave him some information. We told him to go 5 meters, and we said west. He's headed towards the ocean there, it looks like, and that is a vector. Vectors have magnitude Well, let's try to spell the word magnitude correctly. Write this down with me as well and think about it. So the magnitude in this case of 5 meters and direction. And again, an example is a displacement, and we've displaced him right now. We didn't just give him a distance. We've given him a displacement of 5 meters west. Versus a scalar. Scalar actually isn't enough information for the poor guy. We just say 5 meters. And he's like, which way? I guess I get to choose. Which at that point it becomes a vector. But anyway, basically, if we just say 5 meters, it's just a simple scalar. As soon as we go 5 meters west, it's an actual vector. We call it displacement. Oh yeah, this is just simple distance, just raw distance. 5 meters, 2 meters, 10 meters, 100 kilometers. Those are just raw distances. We have to add a direction for them to actually become vectors. Okay, so that's kind of cool. Let's see more on scalars, vectors. Let's see some more here. Let's look at vector in more detail. That was really trying to focus mostly on scalar, although I ended up talking about vectors, which is fine. So vectors have both magnitude and direction. Displacement, which we've got going right here. Well, we got both things going. Distance. So let's just say the only thing we know is, looks like it's a lady biker here, that her distance was 40 kilometers, going on this path. But the actual displacement between start and finish, this is going to be 30K. Oh, but I need, if it's displacement, it's a vector, and it's going to be kind of some southwest direction. And that's the difference right there between distance and displacement. Displacement, you look where you start and you finish and you take the most direct route. Did she actually bike this way? Well, no, there's probably mountains or houses or something in the way. She had to take the road there and then turn and turn, and she had to go 40 km. On this, she didn't actually, well, she did go from here to here, point A to B, but she had to take quite a route to get there. So yeah, a key difference. And yeah, in a displacement, you have both magnitude, so 30 km, and that's just magnitude though, and direction, south, west. Okay, velocity would be an example like we got here. We got this vehicle going 25 meters per second north. 25 meters. Write it down with me here, meters per second. That's pretty quick, by the way. Like, that's really quick, actually. We convert that into kilometers per hour. That'd be a big number, I think. That's interesting. Going north, because we got a map, right? We got a map. We got a map, or we got map-like information, and that's what's going to be helping us out here. Okay, so let's see what else I want to tell you on this here slide. Let's just write out a couple examples of vectors. Vector examples. Okay, displacement. Again, for this lady here, 30 kilometers southwest, exactly how the crow flies. Her actual distance was different, right? Because distance and displacement they're similar, but they're different things. And then velocity for this car here. If you're going to write out a velocity, again, you're going to have a magnitude, so 25 meters per second. That's just the magnitude. Boom. There's our direction. Those are a couple vector examples. Let's check our understanding on this. I'm going to flip the slide. I got a little question for you here. Ooh, scalars and vectors. Cool. That's stuff you know though, right? If I just tell you again, oh, there's a treasure 50 meters from you, that's just a scalar. You're going to go, hey, give me a vector, Phil. Give me a vector and I'll go get my treasure. Okay, so let's take a look at this. Drive 60 kilometers an hour for 15 minutes. Is that a vector? Does it have magnitude and direction? Okay, so is it a vector or is it a scalar? And a scalar would just be magnitude. Is there enough information here is one way to look at this. Go ahead, drive 60 kilometers per hour for 15 minutes. Is that enough information? No. So this is just scalar. 60 km per hour, whether I say 15 minutes or I could say, yeah, go 30 minutes, that still doesn't tell you anything. It doesn't tell you where to go. It might be sort of interesting, right? You could tell somebody, hey, I was going 60 kilometers an hour for 15 minutes. That still might be interesting and a bit of information. But until you add a direction, until you say north or southwest, until you add that, it's not a vector. So yeah, this is definitely scalar. Okay. So we've looked at distance, and we've looked at displacement. We'll let's do a little bit of practice here. Actually, that's my next slide. I just want to flip to my next slide here. So a little bit of displacement practice. There it is. These questions, you could stop the video right here and try them, but again, they're also in Moodle. So you're going to probably want to open up that, that link and then basically have these questions so you can do them. And yeah, take a pause, give them a try right now. There's also a video that shows you how to solve all of these. But yeah, make sure you can do all of these right now. And after this, we are going to look at speed and velocity now. Okay, so you're going to do a little bit of practice questions on distance, which again, a scalar, and displacement. Do these practice problems. If you need to, there's videos on how to solve these as well to watch. Okay, so hit a pause, try these, and then come back to this point because we're going to look at speed and velocity next. Okay, so you're just looking at distance and displacement, which is also related to speed and velocity. So let's start with this sentence here. It took us 7 hours, 30 minutes. So basically 7.5 hours, right? Because 30 minutes is half. 7.5 hours. And we're going to drive 485 km. Think about it. That's looking pretty scalar. It's not a vector yet until we add a map like this. Okay. And so yeah, so this is scalar right here, right? Speed is scalar. And definitely write that down, right? Speed and velocity is our title right now. And speed is just scalar. There is only magnitude, right? So we just say how far, 485K, 7.5 hours. So it's 65 kilometers per hour. That's it. That's just simple. And our notation, we say v/av. So you're thinking, oh, that's velocity, but it's just how we do it, right? And with a vector, we do want velocity. We put this little arrow. And I know the arrow is a little bit messy there, but it's a little arrow. That means it's a vector, v/av. And now we go exactly from where we start because we need our displacement. We don't care about our distance, actually. We want to know where we started and we wanted to know where we stop or where we end. So start and stop. And exactly as the crow flies, apparently, this is 365K north, 40 degrees west. I mean, yeah, you got to know this. You might need to get into a plane or whatever, right? But ultimately, for speed here, we want to get our change in distance. And again, just distance, 485 km. And over our time, 7.5 hours. So it's going to give us a nice kilometers per hour. That's literally what this line is divided by, right? Versus velocity. Okay, so we don't just want distance. What this is right here, when we go delta change in displacement over change in time, 7.5 hours, time is the same. Plug this in, right? So, and again, we're actually not going to give you questions where you got to figure out maps and stuff, but this is just so you can appreciate. So we got 365 kilometers north, 40 degrees. Do write it out with me because you want to start to internalize, hey, this is actual displacement, right? This is an actual vector. Look at, I've got my magnitude, I've got my direction, change in time. We are now going to actually get velocity, right? It's still 7.5 hours. It's just time. And, you know, obviously it's shorter to fly that way. So you're thinking, well, how come they slowed down? Well, because the direct route, right? I mean, it does make sense. 49 kilometers per hour going north by 40 degrees west versus, you know, the distance they drove, which really doesn't give you any information. Hey, I drove 485K and I went 7.5 hours. Doesn't mean anything. But, you know, so therefore it's just speed. Pure speed, 65 kilometers per hour. I went 65K per hour for 7.5 hours. Again, that tells you nothing. But as soon as we get all this information, we're into a vector, right? So yeah, you want to make sure you're clear on that difference between speed. Speed is just magnitude, just pure magnitude, versus velocity. Okay, so let's write it down here, magnitude. It's scalar, so that's what speed is, versus velocity. It's got the magnitude, but it's also got a direction. It's got more information. And, you know, again, if you want to find that treasure that supposedly someone's buried by your house, you're going to want the vector to the treasure. You're going to want to know, okay, so it's 50 and it's north, it's dead north, 50 meters, dead north. There's a treasure there and whatever, just 1 centimeter underneath the ground. I don't know what kind of treasure it's going to be. So this is just going to give you the background, a visual, an example, something you've really lived, right? You know, you've all kind of talked about a weekend. Hey, you know, we drove 400K in, you know, 2 hours, whatever. That'd be really fast. We drove 400K in 6 hours. It doesn't tell people where you went. So you probably actually, you know, especially if they were really interested in your trip, you probably gave them vector information. You probably told them, yeah, we went from Edmonton, and yeah, it's northwest of, went northwest 40 degrees from Edmonton, and oh, you ended up in Peace River. Let's try some model problems. Well, a model problem, and then you got some practice problems to do. So here's your model problem. Use the grasp method, right? Make sure you got your formula sheet always beside you. In physics, make sure you got your calculator. Read it carefully. What information is given? And write this word right underneath it. What information is required? So write the question down in your notebook as well, right? So take a pause. Write the question down. I'm going to solve it, but you know, hit pause and maybe solve it ahead of me. But use the grasp method, given, required, analysis. Do some analysis. In other words, what formula? And I'm thinking it's these two because, you know, we're looking for speed, but maybe it's not those two. But have your formula sheet handy, solve it, and then of course paraphrase. But let's come back here. These are the first two, given, required. I really do often like to start with required. You know, what's the speed? Okay, so V av, right? Don't know it. meters per second. Okay, got to always be in meters per second. You know, I'm looking for my speed. What information am I given? Looks like I got a distance, right? Right there, 550 meters. You're probably well ahead of me, and you should be ahead of me by this point. You should be starting to, you know, hit pause and just try it on your own. Okay, time, 35 seconds. Seems a bit quick, but okay. My speed, or my VAV, which is speed. Start making your mind say, hey, I call that speed. Unknown, meters per second. So gonna look at the question here. I'm looking for speed. So yeah, I definitely need this formula where I go VAV equals change in distance over change in time. Well, I've got the change in distance. It went 550 meters, traveled the distance of that, and I got my change in time, 35 seconds. So I can solve it. VAV equals 550 meters. Put the units there, divided by 35 seconds. See, you're going to get meters per second. Again, this line divided by on your calculator, divided by is per. Okay, so grab your calculator, clear it off. 550 meters divided by 35 seconds. It's going to be 15.71. Wow. Okay, so we definitely do not need all of that, right? Now you can write it out if you like, but look at the question. There's 3 digits there, there's 2. You only need 2 significant digits. So it's either going to round 15, it's either going to round up to 16, or it's going to round down to 15, right? So 15.7 rounds up. So 16. I'm still going to put the 15.71. Just, you know, I want to respect what my calculator put there. A few other things. Meters per second. But again, we only have 2 significant digits in our question. You know, even though there's 3 there, we look for our least number of significant digits, which is 2. So yeah, I'm going to round that up to 16 meters per, say it that way, second. And if you did 16 meters for every second, right, multiply that by 35, you're going to come, it'll be bigger, obviously, than 550, but you're going to see how that also makes sense. So you might want to try that, right? Like, okay, if I did 16 meters in 1 second, it'd be 32 in 2 seconds, you know, so basically 16 times 35. Just check it out. You'll see it comes close. If you do the 15.71, get it exact. But again, this isn't exactly 35 seconds. It's not written in the question 35.000 seconds. That would mean, hey, it's almost exactly 35 seconds. It doesn't say that. It just says, yeah, 35. So they're just using a simple little stopwatch. Paraphrase. Write your sentence. The car is going 16 meters per second. And like I said, you can check this, right? It's always good, especially in math, to check it. Go 15.71, multiply that by 35, right? And of course, we already rounded this a little bit. You're going to see what happens. Just try it. Just make sure you're comfortable doing that in your math and science courses. When you got the formula, you can always check your answers, right? So you know you're right. Okay, there's some more model practice problems now that you need to do. So I'm going to flip that slide. Again, they're right on the screen, so you could hit pause and try them. But they're also in the document, the teaching video practice problems. Again, you're going to want to do all of these. Use the GRASP method on these ones. We also have video showing you how to solve these, so definitely try those. Hit pause, try it. I'm just going to give a quick summary after the pause here of what we covered in our welcome here. Okay, so you want to have done all of the practice problems by now, but also you can just watch the summary too before you do them. We looked at how work in joules equals force times the distance. You know, if you're this person here, I think it was Ted, and you're going to push this, it takes a certain amount of force to get it moving, but once it's moving, that force is pretty constant. But, you know, we want to push it only 1 centimeter versus 20 meters, right? If we want to know how much work, we got to know how much distance. So that makes sense. And you got to be able to solve problems with that. We look at the concept of scalar, 10 meters. Well, if you just tell this guy 10 meters, he's going to go, well, I guess I get to choose. But if we make it exact, okay, so 10 meters west, then it's a vector, right? So scalars only have magnitude. Vectors have magnitude and direction. They're more detailed. A little bit more on scalars and vectors, right? We looked at the difference between distance. So here's, she's taken a 40 kilometers and it actually takes her an hour, right? Versus the vector is going to be her displacement, which happens to be 30K. So this exact displacement right here is 30 km and southwest, right? So again, magnitude and direction, where she starts, where she finishes. And then what if it takes, it's obviously it took her an hour. So her velocity, right? Velocity again is a vector. We got your displacement and then you got your exact magnitude. You got your magnitude and you got your direction with the velocity. So make sure you're clear on that, right? The difference between a scalar or just simple distance and say displacement, right? Because those two, they're kind of similar, but they're different, right? I mean, it's still the same trip that she did. It's not somehow some different trip. It's basically she went from A to B and her distance was 40K, but her displacement was 30K southwest. Her speed, which is also just a scalar, hey, 40K an hour. Hey, that's pretty good, actually. But that still doesn't tell you anything. Her velocity is her exact displacement, 30K, and then over the time, hour, and then, of course, the direction southwest. So her velocity was 30 kilometers an hour. So that's kind of cool, too, right? And again, your formulas for each. And really, you'll see virtually they're very similar. The difference when it's a vector, we put this little hat, we put this little arrow here showing that we gave direction. That's like we gave you direction. So therefore, it's a vector, it's velocity. And last, just kind of really driving this home here, if we just say she's going 40K an hour, that's just scalar. But if we give you the information, that she is going, her final, when we compare where she started, and then we compare where she stops, and we take an exact straight route from point A to point B. So wherever start and stop, that exact, and not just the distance, but also, the direction. So, we're going southwest here. So it's going to be 30 km southwest. And again, her time was an hour. So technically her velocity, well, technically her actual velocity is 30 kilometers per hour. Cool. Okay. Make sure to get all those practice problems done. And that is your welcome to physics. Take care, Science Time.